Good afternoon. Today we will start with ARM instruction set. Now what is instruction set? Instruction set is a group of instructions which are supported by the processor. Right? By reading the instruction set, one knows or programmer knows what are the available instructions and the operands and so on. If any processor architecture, in any processor architecture, an instruction includes an opcode that specifies the operation to perform, such as add contents of two registers or move data from a register to memory, etc., with specified operands, which may specify registers, memory locations, or immediate data. This is general thing we know. So who will supply this instruction set? Instruction set will be supplied by the designer who designed the processor. He supplies the instruction set along with the processor. You will find these instruction sets in the data sheets. So if you write your program which is not present in the instruction set, then that program will not be executed in that particular processor. So if you want to execute the program in the given processor, then you have to use the instructions which are supported in that instruction set that is available with the processor datasheet. Let's see the features of the ARM instruction set. ARM architecture has two instruction sets. We all know why. What are these two instruction sets? It has ARM instruction set, which is 32-bit instruction set. It also has thumb instruction set, which is a 16-bit instruction set. So ARM core supports two instruction sets. One is called ARM instruction set, which is 32-bit wide. The other is called thumb instruction set, which is where each instruction is of 16 bits. Because of this, ARM offers high code density. And one more thing, when we are executing ARM instructions, then the program counter or these instructions are stored in the memory for every after 4 bytes. Why 4 bytes address? Because memory is divided into, each location is having 8 bits. So to store 32 bits, we need four such locations. So when program counter increments, it increments by 4 when it is executing ARM instructions. During that time, it will be in ARM mode. If it is executing 16 bits instructions, then how many locations we need to store the 16-bit instructions? We need 2 locations where each location is having 8 bits. So the program counter increments by 2 when it is executing thumb instructions. During that time, it will be in which state? Not state, mode, thumb mode, right? That we have talked about in previous classes. Next, important features of ARM and thumb instructions are, these are the nice features of ARM and thumb. Most of the instructions are executed in one cycle. In one cycle, all these instructions will be executed. Load store architecture for accessing data from external memory with powerful auto indexing addressing modes. ARM instruction set is RISC instruction set. 80% of the architecture is that of RISC. An instruction set is RISC. In the RISC is a load store architecture that we have said earlier. Load store means all the instructions other than these two operates only on registers. If there are data instructions, data processing instructions, arithmetic instructions or logical instructions and so on, all those instructions, they operate on registers. They cannot directly access the memory. If the data is stored in the memory, they cannot directly access the memory contents. So these are the only two instructions, load and store. By using these two instructions, one can transfer the data present in the memory to the registers in the register bank, or if you want to store the results which are stored in the register bank, which are stored in the registers in the register bank to the memory, we can use store instruction. Inclusion of load and store multiple register instructions. By using load and store, we can transfer data to multiple registers with a single instruction. That we will see in the register, that we will see when we talk about the instruction set. Next, 3 address instructions, 2 source operand registers, and the result register are all distinctly specified. We will see when we say move R1 R2 or add R1 R2 R3. R1 means the destination register, R2 R3 are the source registers. Means R2 register is added with R3 register. I mean contents of R2 is added with contents of R3. That result is stored in R1. That's what this features telling us. Data processing instructions act only on registers. Data processing means arithmetic, logical instructions. They act only on registers. They cannot access the memory. Because of this, these instructions are very fast compared to the CISC instructions. Every instruction can be conditionally executed, which improves the performance and code density by reducing the number of branch instructions. You don't need to write specifically branch instructions, where every instruction, almost all instructions are conditionally executed. If you want, you can execute the instruction based on the flag bits of the CPSR register, current program status register. We have flag bits NZCV. If you remember, the last 4 MSB bits are NZCV. Based on the results of the ALU, these flag bits are continuously updated. Means like negative, if the result ALU result is negative, or if it is 0, or NZC means carry, V means overflow. You can execute these instructions based on the results of the ALU. That is a very powerful feature of this ARM instruction set, which because of this is another reason why we have high code density in ARM processors. Next, the ability to execute a barrel shift operation and an ALU operation of a single complex instruction in a single clock cycle. You can do this together without need additional time for ALU operation. You don't need in one clock cycle, you can perform barrel shift operations along with ALU operations. That is one more powerful feature of this ARM. Next, inclusion of advanced DSP instructions in the ARM instruction set for the multiply and accumulate unit replaces the need of separate digital signal processor. Because of this MAC unit, we have talked about MAC in the data flow model. In the data flow model, we have seen there is one hardware called MAC, which stands for, what is this? Multiply and accumulator. Multiply and accumulator. Multiply and accumulator means it multiplies 2 numbers and it adds that result with the accumulator answer. Means this is very useful, particularly if you are implementing DSP algorithms. In the DSP, what we do, almost all the DSP, if you break down any algorithm, finally any computation reduces to multiplication, addition, multiplication, addition. That's all, right? So we have a separate MAC unit for implementing DSP algorithms. So because of the MAC unit, you don't need a separate DSP processor. all the DSP related algorithms can be implemented in the or because of this MAC. Otherwise, then too you can implement, but it takes a lot of time for the DSP algorithm to execute. But anyway, we have MAC, so that avoids the additional DSP processor. Implementation of co-processor instruction set with extension of the programming model. If you want, you can extend the instruction set with the co-processor. The thumb instruction set is 16-bit compressed representation of the ARM instruction that provides high code density. These 16-bit thumb instructions, these are widely used instructions. We put in 16-bit, rarely used instructions are 32-bit instructions. Next. So here in this slide, we are seeing the classifications of ARM instruction set. There are many instructions we can classify for better understanding are based on what functionality those instructions are delivering. We can classify instructions into the following. Data movement instructions. Data movement instructions means data is moved from one register to another register. Those instructions are categorized under this data movement instructions. The second type is data processing instructions. Data processing instructions means we have some data, we want to add them or subtract them or compare the data or multiply the data, or we can perform AND operation between two data. These are all data processing instructions. So these data processing instructions are further classified into these four types: arithmetic logic instructions, barrel shifting operations or barrel shifting instructions, comparison instructions, multiply instructions. These are the four subcategories under the category called data processing instructions. Next, branch instructions. Branch instructions means branch means normally we call a function, then execution goes to that particular function. Like that, branch instructions means it is like jump instructions. Normally program executes like this. First line is executed, after that second line, after that third line, and sometimes based on this jump instructions are called branch instructions. The execution disturbs, it moves to some other new location. Okay, like jump instructions are examples of branch instructions. Next, load and store instructions. Load and store instructions means the instructions which access the memory. Either data is moved from memory to the registers or from registers to the memory. Those instructions are classified under load and store instructions. Next, program status register instructions. Set the values of the conditional code flag and so on. Next one is software instructions, software interrupt instructions. By using these instructions, we can issue interrupts, that is software interrupts. We have two types of interrupts, software and hardware. Hardware interrupts are generated by the peripherals, whereas software interrupts are generated by instructions like add, subtract. Add, subtract are not interrupts. Like instructions, like instructions, we can, by using these instructions, we can generate interrupts. Those are called software interrupts. Means instructions which are generating the interrupts are called software instructions. Next, we begin with the instruction set. Let's begin with barrel shifter operations. There are some significant operations performed by barrel shifter. Let's see what are the operations that are available with the barrel shifter. Now see this diagram. This is the arithmetic logic unit where all the arithmetic and logic operations are performed, and it is a 32-bit ALU, and it it receives two operands. One is directly from the register bank. You think there is a register bank here. Register bank means group of registers. How many registers are there in user mode? There are R0 to R15, totally 16 registers. Along with the 16, we have CPSR, current program status register, right? CPSR gives the status of the program which is being executed. Status means we all know the last 4 bits tells the status of the result of the ALU. The first 5 bits, they talk about the state of the processor, like that, right? And the second operand also comes from the register bank, one of the registers, R0 to R15, one of the registers, but second operand passes through the barrel shifter, where this barrel shifter does the following operations. This barrel shifter does this following operations. LSL means logical shift left. These are the operations that are supported in the barrel shifter circuit. Barrel shifter is just a combination circuit. In the combination circuit, we can perform these operations. Logical shift left, LSL, this is the instruction. LSL means logical shift left, this is the description. And this is how this is what happens when you use this instruction. X left shift Y means X operand which is left shifted by the data present in the Y operand. Okay. When we have some data X here, that will be, if you left shift that X by Y, then the data present in X, that data will be left shifted by how many times? With the data present in Y. Let's say number 8 is present in X and number 2 is present in Y. So 8 will be left shifted by how many times? 2 times. Why? 2 is present in Y. That is what this left shift operation is. LSR means logical shift right, and this is the result. This is how this instruction executes. ASR means arithmetic right shift, and this is the X register, Y register. In between we write ASR. ASR stands for arithmetic right shift. This is instruction of mnemonic ASR, and this is what happens. X will be right shifted by the data present in Y. That many times X will be right shifted. ROR stands for rotate right. So X, ROR, Y. This is how we implement this ROR operation. These are the instructions supported by barrel shifter. When you use these instructions, the corresponding action will happen not in ALU, but in barrel shifter. When you use these instructions, the execution will not be done in ALU. It will be done in the barrel shifter. That too, only second operand will be affected. Means you can apply these operations, these instructions only to the second operand. First operand is very direct. You may see here. First operand comes from the register bank, from one of the registers directly to ALU as first operand. Whereas second operand can be shifted and result will be passed to ALU as second operand, right? And what are the operations that are performed by barrel shifter? This many operations: LSL, LSR, ASR, ROR, RRX. RRX means rotate right extended, and this is how we use this instruction, and the result is, this is how the result will be affected. Let's understand these operations a little bit more. Now see LSL, the first one. LSL means logical shift left. Logical shift left, example is given here. Logical shift left by 4 units. Means this is the data present, means this is the register which is containing, this is the second operand. This is the second operand, and this is the second operand. The second operand data is undergoing logical left shift by 4 units. 4 means this 4 is to be stored in which variable? Which variable Y? this original data is present in which variable? X. X is the second operand, that is this second operand. So X comes here, and in the barrel shifter, uh, logical shift, right shift or left shift? Is it logical left shift? Logical left shift happens in the barrel shifter. How many units? That is given in Y. If you store Y, if you store 4 in Y, 4 many units will be shifted logically right. Sorry, logically left. Now see, this is the data present in the X second operand. Before it, this is the actual data which is present in the second operand. So that second operand passes to barrel shifter. This is the actual X that passes through barrel shifter. In the barrel shifter, what happens? That shift example. This is example in which we are shifting this X by 4 units, 4 bits. So what happens? Of course, that X is a 32 bit. All the registers are 32 bit wide, and this is fixed in ARM. All the registers are 32 bit. ARM 7. We are talking about ARM 7. Now see, let's say this is the data present in X. After shifting left, what happens to the result? What happens to the result? This is the X that enters into the barrel shifter. This is the result, that this is X that enters into the barrel shifter. While it leaves the barrel shifter, this will be modified like this. This will be modified like this. This is the output of the barrel shifter, which goes into the arithmetic unit here. Which goes into the arithmetic unit here. Now see here, we are logically shifting it left by 4 units. 4 units means the first 4 bits will become next 4 bits, means these 4 bits will come down here, these 4 bits will come down here, and so on, so on. These 4 bits will become the last 4 MSB bits. Whereas what happens to the LSB 4 bits? They all become 4 zeros. If you are shifting it by 5, then you will get 5 zeros at the beginning, and these all bits, whatever the bits, either zeros or ones, in what order, they all come like this. These 4 bits will come down here. This first 4 bits will occupy the positions, these positions. These 4 bits will occupy these positions. So barrel shifter takes this data and modifies like this. Okay, that's what this instruction does. This instruction will be executed in the barrel shifter. This is equivalent to left shift in C. And the next instruction is LSR. What is this LSR? Logically shift right. The same thing, but shifting is done towards the right side. And here we are considering example in which we are shifting it by 4 bits. 4 bits means the MSB bits will be filled with 4 zeros. If you write 7 here, these 7 bits will be zeros, like that. And this 4 bits, MSB bits will occupy these places, and so on. Okay, and this will be dropped. Whereas here the MS bits will be dropped. Next, it is equivalent to right shift. Next, see, the next instruction is ASR. These are the instructions supported by what? Barrel shifter. ASR, arithmetic shift right. ASR stands for arithmetic shift right. Arithmetic shift right by 4 positive value. Now see, ASR, if you look at this ASR, it may be sign and number. Okay, means arithmetic shift, what is this? Arithmetic shift right, arithmetic right shift or arithmetic shift right. It applies on X where X is allowed to be signed. Where X is signed means it may be positive number or negative number. Okay, arithmetic shift right, it applies on X where X is a signed number, means you can have a positive number or negative number. Now let's see ASR. If it is a positive number, for a positive value, if it is a positive value, what happens is, this is the value that enters into the barrel shifter after processing. What processing? ASR, arithmetic shift right. This is what comes out of the barrel shifter. Now see what happens. These 4 bits will occupy the LSB bits. These 4 bits will be dropped. These 4 bits will be dropped. In this case, they are zeros, whatever. They may be any values. All those 4 bits will be dropped because we are right shifting by 4 units. If it is 7, then 7 bits, first 7 bits will be dropped and so on. And at the end, in the result at the end, MSB bits, 4 zeros will be added. 4 zeros will be added if the X means the register value that enters into the barrel shifter, that X is positive. That X may be negative because this arithmetic shift rate instruction operates on signed number. Next, if it is negative, then how what happens is, this LSB bits will be dropped and these 4 bits will be these 4 bits will come here as LSB bits and so on. These MSB bits of the register input contents will come down here, and the MSB bits, first 4 MSB bits will be filled with ones. With ones, these are constants, 1 1 1, so that it is a negative number. And we all know equivalent to right shift is sign division by power of 2. Right shift means we are dividing it by power of 2. Left shift means we are multiplying with powers of 2. Next, another instruction is ROR, rotate right. This is rotate right instruction, and rotate means there is nothing dropping here. In previous instructions, in either left shift right or left shift left or arithmetic shift right and so on, you are dropping either lower bits or higher bits. Whereas in rotate right, we are not dropping anything. We are moving. It is like a circular shift. We are moving some bits, move towards a clockwise direction and so on. No bit will be dropped here. We are not losing any data. Example, rotate right by 4, bit rotate with wrap around. Now see, in the rotate right means all the bits will be rotated by how many bit places? 4. Here we specified 4, that's 5. 4 bit places will be rotated. Means these 4 bits will come here, these 4 bits will come here. These 4 bits, they move around and occupy the MSB place. So after this, what happens is, the LSB 4 bits, 4 means this 4, we are specifying it. These 4 bits will become LSB 4 bits in the input of the barrel shifter. They become this LSB 4 bits, they become MSB in the output. And next LSB, next 4 bits, they become the actual LSB. Means they are not dropping, they are moved and appended at the end. And this is what is the result of the rotate right instruction in the barrel shifter. Next, another instruction is RRX. RRX is rotate right extended. Extended means here we include the carry bit. Carry, this is the carry bit, where we have that carry bit in the CPSR register, current program status register. That carry bit is used as 32. There are total 32 bits. This carry bit is used as 33rd bit, and this is what happens when you rotate it right. There is no specify. We cannot specify any number like this. Just this itself is the operation. RRX, rotate right extended. What happens is, this carry bit will come here as 31st bit, and so on, so on. The LSB bit of the first LSB bit, they go to the carry, means carry bit will be affected. Carry bit in the CPSR will be affected with what? The LSB bit of the input of the barrel shifter, right? And carry bit of the CPSR register will transfer to which location, which bit place? 31st bit place. You may notice the numbering 0 to 31 and so on. Like this, these are shifted. Everything else is one bit. This will come here, this will come here. Every bit will be shifted towards right by one position, whereas this LSB bit, they occupy the carry bit in the CPSR. Carry bit in the CPSR, it becomes the 31st bit or 32nd bit in the 31st bit according to index 0, or 32 last bit in the result, in the output result of the barrel shifter. So these are the different operations that are offered by barrel shifter. Now let's see how this can be used. These are the general syntax. Shift operations, logical shift left, RM by shift immediate value, means we can use immediate value. Immediate value means RM. The second operand need not be a register. It can be immediate value. Here we have immediate value. Here we are using register. You can use either RM left shift left, a register. Here we are using RM left shift left. Hash means this is for immediate value. You can use some number here. 2 means that becomes immediate value, means the RM contents will be left shifted by 2 bits. This 2 we are specifying 2, that is not coming from the register, that is direct value called immediate value. Here, that how much this RM should go should be left shifted, that is stored in the register. In the same way, for all the operations, we can do this. For logical shift right, also we can have immediate value or how much shift that may come from the register itself, like this. Next, we will see one example here. Now see, let's see this example. Let the data in R1 equal to, this is the data which is 0x, it is hexadecimal number. There are 1, 2, 3, 4, 5, 6, 7, 8, 8, 4, 32. It is a 32-bit binary. The first 4 bits are zeros. Next 4 bits are 1, 0, 0, 0. Is it so? Yes. Remaining all are zeros. First 4 zeros. Next 0, 0, 0, 1. And remaining all of them are zeros. That is R1. And what is this R2? And what are these R1, R2s? R1, R2s are the registers available in the ARM, like R0, R1, R2, R3, and so on, up to R15. We can use these registers to store the data that is to be processed in the ALU. And what is R2 containing? 0, 0 at the end 4 means the first 4 bits are 0, 0, 0, 0, 1, 0, and remaining all are zeros. And what is R3? 0x. FF means the first 4 bits are 1, 1, 1, 1. Next 4 bits are also 1, 1, 1, 1, and remaining are zeros. That is what is R1, R2, and R3. Now the question is, after executing the instruction move R3, R1, LSR, R2, data in R3 equal to this, R1 equal to this, R2 equal to this. Now let's see what is this instruction. This is the ARM instruction. Move means it is movement, data movement operation. See, this is the destination register. The first operand is the destination. There is the mnemonic. Okay, there is the mnemonic. Move means mnemonic. The first operand is the destination register. Second operand is the source register. And third operand is by what amount this source register contents are left shifted. This is the left shift right. No, logical shift right. Logical shift right. Is it logical shift right or left shift right? So sorry, logical shift right. So logical shift right by the contents of R2 means what when you execute this instruction, what happens is the data of the data present in R1 that is logically shift right, that is shifted right by how much, that much. What is present in R2? What is present in R2? 4. So data in R1, this data will be right shifted by how many bits? 4 bits. Okay, 4 bits. That result is stored in R3. That result is stored in R3. Okay, that result is stored in R3. Now let's see. Initially R3 contents are this. They will be erased. New values will be updated with R3. Updated in R3. Now see the description. The data in register R1, the data in register R1 is logically right shifted by the data that is there in R2. That is there in R2 means how much is there in R2? 4, which means this is R1. This is R1 is written here. That is right shifted by 4. 4 means what happens? You think in terms of binary. 0, 0, 0, 0, 0, 1, 0, 1, 0 like this, like that. So this entire 4 bits here, they will be right shifted. After that, this is what results. So that will be moved to R3. The previous contents, which are this, they will be erased, and new contents. What are the new contents? This will be stored in R3. So move this value to register R3. So R3 becomes this much now. Previously it was this. After executing this instruction, it has become this. But data in R1 and R2 remain unchanged. Nothing will happen to the data in R1 and R2. Only R3 will be affected because R3 is the destination registers, whereas R1 is the source register and R2 is the R2 containing how much right shift has to be done. That is specified in R2. Next. Next, data movement instructions. So far we have seen what? We have talked about barrel shifting operations. Barrel shifting operations. Now we will talk the general instructions in the instruction set. These are the general instructions in the instruction set. What all the instructions offered by barrel shifter, they all can be applied to second operand. We cannot apply those barrel shifting instructions to the first operand because first operand directly enters the ALU, whereas second operand that passes through the barrel shifter. So you are free to apply barrel shifting instructions to the barrel shifting instruction only to second operand, right? So barrel shifting operations are valid only to ALU operations, means data processing instructions.